Hi everyone, my name is Qiskit Fall, and in this notebook we'll be looking at Bell states in quantum computing. This is my outline. So, take you through Bell state analogy, Bell state types, Bell state applications, some jargons in quantum computing, a quick Jupyter guide creating a Bell state, interpretation, conclusion, and references. So to Bell state analogy, before we create this analogy, let's first understand what a Bell state is at the basic level. So Bell states are special types of entangled states that involve two qubits. And before you can understand Bell states, you must understand the phenomenon known as quantum entanglement in quantum computing. So in quantum entanglement, there are two quantum states or two quantum bits or two qubits that are maximally entangled, in that the effect on one qubit would affect the other. So that is a bit about quantum entanglement in Bell states. So let's look at this analogy. Imagine a special quantum pill that can be split into two halves. Each half represents a qubit. So remember, in entanglement, two qubit ions are maximally correlated or connected. So let's imagine this pill, full medical pill, that when you split it into half, each half represents a qubit. So let's take notes some of the key properties of our quantum pill. In this case, the qubit we'll be using. So in this case, a quantum pill. So before observation, so the color represents the superposition. So before observation, each pill half exists in a superposition of blue and yellow. I can use blue and yellow. Before measurements, they're in a superposition of blue and yellow. That is each pale half. Then the measurement, when observed, each pale half instantly becomes either a yellow or a blue. Then entanglement is when the two halves of the pill are entangled, meaning their colors are correlated in specific ways. So going down, we are looking at the qubit state in our analogy. So for a state of 0, it will be represented by blue, and for a state of 1, it will be represented by yellow. And for a state of superposition, it will be a blend of the two. So let's imagine another scenario where there are two individuals observing these changes in the quantum pill. That is, whether it falls into a state of a classical bit or it's in a state of superposition, where these two individuals observe the changes at their various ends. Yes, they are not in this scenario, they are not supposed to be in the same location. So they're at different locations. So Alice in this case is in New York, Alice is in blue, and Bob is in Tokyo. Bob is red in color in this image. Okay, but let's not forget the pale colors are blue and yellow. Blue for 0 state, yellow for 1 state. Okay. So Alice and Bob are the observers and not the pills themselves. So each of them has a device to measure the color of their pill half. Okay. So measurement process. When Alice measures her half, it instantly affects Bob's half, regardless of distance. Mind you, one is in Tokyo, one is in New York. And if Alice's half turns blue, Bob's will always be blue. If Alice's Alice's color is yellow, Bob's will always be yellow. This happens instantaneously, faster than any classical communication between New York and Tokyo. Let's also not forget, let's remember that the pale halves represent the entangled qubits. Alice and Bob are the observers measuring the states of these quantum pale halves. And the instantaneous correlation between the halves, regardless of distance, illustrates the non-local nature of quantum entanglement. So this is an analogy. So now that we understand what quantum entanglement is, still let me go over again. Quantum entanglement is a phenomenon where two or more qubits become correlated in such a way that the quantum state of one qubit affects the other. It cannot be described independently. So there are four main types of Bell states. These have been graphically represented in circuits for us. Okay. So we have the phi plus state, which is this. We have the phi minus states, which is this. Then we have the psi plus states, which is this. And we have the psi minus states, which is this. So in normal quantum computing, there are gates, qubits coming together to form the circuits, right? Okay. So these states of entanglement, we achieve them using circuits. Yes. So there's a notebook attached where we'll go through it to fully understand this. But for now, let's just focus on these. So this is a psi symbol, the 0, 0 representing the qubit, 2 qubits. So this one tells us that if this qubit is turned off, meaning the other one is automatically off. If this one says, so this one is positive and this one is negative. So the negative just talks about the phase change, but we will delve deeper. So let's look at the phi plus. So this is an equal superposition of both qubits being in the 0 state and both qubits being in the 1 state. So if you measure either qubit, you have 50% chance of getting a 0 and 50% chance of getting a 1. However, whatever result you get, you know that the other qubit will have the same results. Good. So let's bring it to real life analogy. We call this the perfect pill because earlier on we were using the pill analogy. So in this perfect pill, it's like Alice and Bob each taking each half of a mood stabilizing pill. So if Alice feels calm, which is the blue, in this case 0 state, Bob also feels calm. So if Alice feels energetic, the yellow, which is the 1 state, Bob also feels energetic. So their mood always match no matter the distance. So we can call this the perfect pill, which is also known ideally as the phi plus state. Then we have the phi minus states. Remember, all this thing is done with a quantum circuit. So we have the phi minus state. So this is similar to the phi plus state, but with a negative sign before it. The negative sign introduces a phase difference between the two terms, which is crucial in quantum mechanics. Like the phi plus, measuring either qubits gives a 50% chance of 0 or 1, and the results will always match. Let's use a real life analogy. We can call this the quantum twins pill. So imagine that one pill makes Alice and Bob experience the same mood, but they arrive at different times. So if both of them end up becoming calm, which is blue, Alice might have gradually relaxed while Bob suddenly mellowed out. qubits. So yes, they all become calm, but one's calmness occurs faster than the other. So that is a phase change we're looking at here. So that's for the phi minus state. Then we go to the psi plus state. Remember, there's a difference between the phi and the psi. Good. So we come to the psi plus state. So in this Bell states, there's equal superposition of the first qubit being 0 and the second qubit, and vice versa. So if you measure either qubit, you would have 50% chance of getting 0 or 1. However, whatever result you get, you know that the other qubit will have the opposites. You will have the opposite. So that's with the psi. So real life analogy, we can call these ones the complementary color pill. So this is like a balance pill where one person's energy is always complemented by the other's calmness. And if Alice takes a pill and feels energized, which is the yellow, Bob's half makes him feel calm, which is the blue. So they are always in a perfect balance, one active and one relaxed. Unlike the other one, unlike the fire where it's either both of them are relaxed or both of them are energetic, right? So we have the last or the fourth Bell state, which is a psi minus state. It works along the similar lines as the psi plus. Like here too, there is a phase difference. So this is similar to the psi plus with a negative sign before the 1-0 state term. Again, this negative sign introduces a phase difference, and so it means that the actions may occur at the same time, but one will lag. One's action will be felt before the other. So we can term this as a quantum opposite pill. So think of it as an advanced version of the balance pill. Not only does it make Alice and Bob experience opposite states, no, but it also influences how they transition between states. If Alice's energy gradually increases, Bob might experience a sudden onset of calmness. So these terms use the perfect match, quantum twins, complementary colors, and quantum opposites are terms I coined for this one, just for the analogy. But their real names are the psi positive states, the psi negative states, the phi positive states, and the phi negative states. So therefore, psi phi, so psi positive, psi negative, phi positive, phi negative. Okay. So after we've created all these entanglements with the circuits, what's the end to this? So we then look at the applications of Bell states. So Bell states are fundamental in other areas, but predominantly these three. One is the quantum teleportation. So it allows the transfer of quantum states from one location to the other using classical communication and shared entangled state. The second one is super dense coding. The name speaks for itself. It enables the transmission of two classical bits of information by just manipulating only one qubit of an entangled pair. Then it can be used in also quantum key distribution. So it provides a secure method for sharing encryption keys with security guaranteed by the laws of quantum mechanics. So if you forget anything, don't forget the application, which is the teleportation, super dense coding, and quantum key distribution. I'll be talking about quantum. So for this fourth point in my outline, I've explained some of the jargons used in the quantum computing field. So we have here qubits with some pictures. We have quantum gates, we've already explained that, but we need them here too. Entanglements, that's basically what this notebook is about, quantum circuits and all. Okay. So for the fifth one, I'll walk you through a notebook on how to create a Bell state. But before then, I want you to know that ideally these things should have been or should occur in a quantum computer hardware, but it's so hard to come by, so we use simulators to run these things to see the results. Okay. So for this Jupyter notebook, we start by installing the necessary libraries, and the language used here, the programming language used here is Python. Then you can, this one is, it depends on you. You can inspect whether your installed library has actually been installed, right? So you do some inspection, but that's all up to you. But it's a key step, because sometimes your code runs, but you realize you're unable to still continue with the other runs because there was a partial installation. So this code helps you to tell, okay, if you've done a full installation. Then after you import some packages from the libraries you have installed, then you create a quantum circuits. So earlier stated, I said a quantum circuit consists of what? A qubit and a quantum gate. So you create a quantum circuit with 2 qubits and 2 classical bits, because you know that no matter what, even after the state of superposition, the qubit must collapse into a classical bit, either 0 or 1. So even as you are creating a circuit with 2 qubits, you have to also include the 2 classical bits so that the measurements can be really read well. Here, yes, after creating the quantum circuit, we apply classical gates to create we apply quantum gate to create the Bell states. So first off, we apply the hard-math gates. So the hard-math gate, what it does is that it puts the qubits in a state of superposition. Then we apply the CNOT gate on the first qubits. We apply the CNOT gate with the first qubit as the control and the second qubit as the targets. So what the CNOT gate does is that it entangles the 2 qubits. So it entangles the control qubits and the target qubits. Okay. Then after, we measure the qubits. So we measure the qubits, we observe. So to observe the quantum state, we measure the qubits. So here, this measures the qubit 0 and stores the results in a classical bit 0, and measures the qubit 1 and stores it in a classical bits of 1. Then after, we simulate this. So simulating is basically ideally running it in a quantum hardware, but in this case it's not really a hardware, it's a simulator. So all this must be simulated before you can see the results. So let them visualize our result. So this is the circuit we created. So this is the H is the hard-math gate. The X so the H is the hard-math gate, and you can see another gates. There's the CNOT gates. Then the M showing the measurements or the collapse states of our qubits. Then we print the counts. So at the end of the day, this is the result it shows. Consider for the 0, 0 state, after 1,000 shots, after 1,000 counts, 539 was found to be in the state of 0, 0, and after 1,000 counts, 485 were found to be in the state of 1, 1. So let's go to the interpretation of this result. So the result is typical of a Bell states measurement in quantum computing. These are maximally entangled quantum states of 2 qubits. There are 4 Bell states, but this result looks like it's from one of the 2 specific Bell states. That is the phi positive and the phi negative. Yes, because in the phi positive, once one qubit is in a state of 0, it automatically affects the entangled pair to also be in a state of 0. And once the qubit is so that basically that is it. So with the result, you can see that 0 0 we go 539, 1 1 we go 485. So meaning it just has to be phi positive or phi negative. We are not so certain because the 0011 are still representing the phi's. So you cannot just say it's just phi positive. So to be on the safer side, you can just say it's for phi positive or phi negative. So this is phi positive and phi negative. So this is the explanation. The measurement shows only 2 outcomes, 00 and 11. This is consistent with Bell states phi positive and phi negative. And in an ideal Bell state, you would expect exactly 50% of the 00 state and 50% of the 11 state measurements. And the actual results are 539 versus 485, which is close to a 50-50 split with some statistical variation. So what's the significance of all of this? So this result strongly suggests that the qubits were indeed in a Bell state. The slight imbalance between the 00 and 11 states could be due to a normal statistical fluctuation, or B, it could be due to some small imperfections in the quantum circuits, which is expected, or C, a decoherence or noise in the quantum system. So in total, putting the measurements together, you have 1124, which is a common number in quantum computing. So Bell states are a cornerstone of quantum mechanics, showcasing the mind-bending concept of entanglement. These special quantum states, which are particles, are so deeply linked, they act as one regardless of distance. And it may seem strange at first, but don't be discouraged. As you explore further, you would find that understanding Bell states opens doors to fascinating quantum technologies. Keep your curiosity alive, and you are at the beginning of an exciting journey into the quantum world. These are my references. Thank you.